Now, dear student, chapter number 6, work, energy, and power, and we have the topics for the discussion here. First, the kinetic energy and the relevant formula. Now, the next, work energy theorem under the constant force. Already we have discussed the work done under the constant force. And also we have the work energy theorem under the variable force. So we are just getting the different type of the concept formula here, and we will solve also the numerical on these concepts. Now we are just getting the meaning of the kinetic energy. The energy possessed by a body by virtue of motion is called the kinetic energy. Okay, now the several examples we have. Energy in a moving ball, energy in a moving vehicle, energy in flowing water, energy in flowing water. So all the kind of the moving body having its own energy, that is called the kinetic energy. Now the basic formula we have, formula detection. So we are just assuming the one of the basic case here, that we are just putting a force on an object. So what will happen? So this is the position that object is lying at the A, and we are just applying the force on it. So easily on inside the ninth class you have also discussed the basic formula, and the ball is covering the change in position, that is called the S, the displacement S is there. Okay, so how we are just making the assumption. So whenever we are just making the basic concept of formula, that is work done. So how we are just assuming the meaning of the work done. Work done means work done is equal to force into displacement. That's the one of the general equation we have, and the force regard the ma. So work done is equal to ma as we have. That's the one of the general equation we have. Now we are just using the concept of the v square minus u square is equal to 2as, and we are just separating the meaning of the as. V square minus u square upon 2 is there. Okay, and we are just assuming the here that initially the object at the rest, so the u is equal to 0, and it acquires the velocity from the a to b. Okay, so probably we are just getting the meaning of that v square by 2. So this is the part of the that mean as we have. Now we are just use equation number third in equation number 1. So what we are just getting, as we are just getting the equation number 2, equation number 2. So work done can be stated in the part of the kinetic energy, because we are just writing in the sense of the kinetic energy. So easily we can write that m at the place of the as, that we are just writing that, and we are just getting half mv square. So this is the general formula we have, general formula of the kinetic energy we have. Okay, so what are the basics we have? Already we know the unit of a kinetic energy. Kinetic energy in the SI system, it having its own unit, that is called the joule. Okay, and if I am just saying that what is the part of the dimension you have, so easily you can write the meaning of the dimension m1 L2, and that is a t minus 2 you have, and probably it is a scalar quantity, a scalar quantity. Okay, so these are the basics we have about the kinetic energy. Now we want to discuss the kinetic energy, that means work energy theorem in the under the action of a constant force. Now I am just applying the constant force on a body. So the what kind of the possible statement which can I write here? The work done by the net force acting on a body is equal to the change in kinetic energy. Work done by net force on the body is equal to the change kinetic energy. Okay, so easily we are just assuming that simply we are just making the concept of the object is there. So whenever we are just applying the force on it, so we are just applying the constant force we have. Now this is the kind of the constant force we have, and probably it creates the acceleration in it. So acceleration is there inside the object is there. Okay, so this is the position of the object we have, and we are just assuming here also that suppose it having its initial velocity that is called the u, and it acquires slowly it's moving in a forward direction in and acquired the final velocity that is called the v, and during this process it acquires the displacement that is called the s we have. Okay, so what actually we are using that by use of third equation of motion. So what actually we are writing, v square minus u square is equal to 2as. This is the first that mean equation we have, and as we are just multiplying this equation by the multiply equation 1 by factor m by 2, and here we are just also assuming the mass of the object is the m we have. Okay, so these are the basic assumptions which we have to be considered before starting the derivation. Okay, so multiply, we are just multiplying it m by 2 with the each term of the equation number 1. Mu square by 2 is equal to m by 2 is to multiplied by the 2as. So I am just cancelling out all the terms, and here we have the basic formation of the ma. So the ma can be considered as a m and a both can be considered as a group, that is the force, meaning of the force we have. Okay, so we will club together them, and I am just writing that mv square by 2 minus mu square by 2, that is called the f into s, and the meaning of the f into s is sense of the work done we have. So I am just putting it here as a w, and this is the portion of a final kinetic energy, this is the portion of a initial kinetic energy. Okay, so we can also make the changes here. Now kinetic energy final minus kinetic energy initial, that is equal to the work done. So this is the basic general proof of the work energy theorem by the mean of the constant force. Similar, we are just getting, we have also completed one of the topic that work done by the under action of the variable force. So similar, we have the meaning of the work energy theorem under the action of a variable force also. So the simplest statement which I have taken here, that the work done by the variable force acting on a body is equal to change in kinetic energy, that is k final minus k initial. So already we have discussed in the lecture of the variable force, we are just assuming the force is acting along the direction of the x in the variable manner. Okay, so we have discussed that it makes the consideration of the change in position from x initial to x final. Okay, and for the calculation of the work done, we have assumed that we are just dividing the displacement in a small strips. So we are just taking one of the strip, okay, which having the very small portion, that is called the delta x turns to 0. Okay, and we have applied the integral on it. So we were getting the meaning of the work done by the variable force in the sense of that work done is equal to integration of x initial to x final. Okay, and f dx. Okay, so we have made the certain changes in this paragraph in this statement, and finally we got the formula that as the variable force is acting on an object, so it make the change in a positions. Okay, and the changes in the position from x initial to x final, so we are just making the sum up of the integral, or we are using the concept of the integral term here. So here I am starting with the concept of the kinetic energy, that is called kinetic energy is equal to half mv square. Now I am just making the derivative of by the dy by dt on the both side of the equation, and here we have also that dy by dt of the portion that is of mv square. Okay, So how can we assess it? Here we are just using the same notation in the left hand side, dy by dt, and we are just making the dy by dt of the v square is there. So the m is a non that means constant part we have, so we are just keeping it outside, and we are just making the pure derivative of the v square. So first we will use the concept of the power notation, then we will apply the derivative on the v. Okay, so I am just making that dy by dt of k 1 upon 2 dot m is there, and I am just reducing the power, so it makes that 2v first, and then we are just applying the derivative on the variable that is v, and dy by dt of the v makes the concept of the that mean acceleration. So this is the proper derivation of the part we have. Okay, now how we are just making the changes in it, as we can cancel out the 2 to 2. Okay, so dy by dt of the k with regard of mv, and here we are just getting the we want to make the changes in the term of the position, so I am just representing the velocity as dy by dt of the that means displacement. Here just I have made the change, and dy by dt of the v I am just making the changing as if a part of the a. So ma is make the concept of the f, and we have the dy by dt of that is of x. Okay, so now we are just able to remove the concept of the dt from the both the sides. So finalize, I am just making the change in the equation, that is dk is equal to f dx, and here just I am making the changing or applying the limit on a portion, that is equation number 2. Now I am just making the applying the limit here. So here the kinetic energy changing from k initial to k final. Okay, the lower limit is equal to k initial, and the final limit is of the integral, that is for k final. Now here also the position is changing from x initial to x final we have. Okay, so how we are just making the change? So we are just assuming the function inside the integral, that is k raised to 0, so it having its own meaning, and where we are, whenever we are just solving it, so it makes the final assessment that k final minus with the concern of the applying of the unit, k final minus k initial is there, and f is the non-relevant term we have. Generally it available in the part of the displacement. Okay, already we have done the one of the question on the variable force, so we are just getting that x final minus x initial. So here you must pay the attention the product of the force and the displacement regard the work. Okay, so we are just further getting the meaning of the change in kinetic energy as we have applied the concept of the variable forces. So this is the relevant proof of this theorem we have. Okay, so this is the portion of a kinetic energy, and now we want to that attempt one of the problem on the concept of the variable force, so we can easily grasp the more concept. Now to specify the more that mean clarification about the variable force concept, now I am just making the solution of the example of the 6.6, which is given on the page number 120 in the NCERT book. Okay, so you must go on through it. A block of the mass of that mean 1 kilogram moving on a horizontal surface with the speed of v initial is given, that is called the 2 meter per second, and enters in a rough pitch of x is equal to 0.10 meter to 0.2.01 meter. The retarding force that is a type of a friction we have on the block in this range is inversely proportional to x, that is the change with the length, okay, over a range. And the meaning of the force which is given inside the question which we have, the retarding force that is equal to the minus k upon x, and the pH which is available from 0.1 less than x less than 2.01 meter. Okay, and the meaning of the k is available in the part of the joule we have. Okay, so how can we start this one problem? So we will use the concept of the variable force. Okay, so we are just using the basic equation that k final minus k initial is equal to integral of x initial to x final, and the meaning of the f and the dx is there. So this is the general equation we have, and what kind of the that mean query we have. Now the query we have that find out the k final and the v final v. v final for an object. Okay, so easily we are just using this one simplest formula, and we are just applying all the things here. Now k final can be state is equal to k initial, as just making the transferring of the term, plus of that x initial to x final or f dx. And further little bit I am just making the changing of that part, that means k final, k initial can be converted as that mv initial square by 2. Okay, this is the first change which I have made here. And x initial to x final with the concept of the f dx we have. Now we are just putting the all the value and getting the meaning of the k final. Now what is the mass of the object we have? That is simply the 1 kilogram. So 1 by 2 into 1 into v initial, which is given to us, that is 2 meter per second. So 2 square is there, plus now the one of the basic integral we have x initial, that is called the from 0.10 to 2.01 meter. Okay, and the meaning of the force of the friction we have here, we are just assume that force of friction, because work done under the action of a force of friction. Okay, so whenever we are just applying the value, so it comes in the part of the negative sense. Okay, and the meaning of the force of friction we have given, that is minus k upon x. So here just I am just making the part in the bracket, and the k having its own value, that is 0.5 is to be divided by meaning of the x we have. We don't have the meaning of the x, so we are just putting the x is at as it is here and making the basic integral. So here we have the basic formula, that 1 upon x generally regards as a log x. Okay, integral of 1 upon x dx generally regard that with the concept of the Napierian log, that is called the log base e, that is log x. Okay, so this is the general formula which I will use here. Now I am just solving the portion, that is this fraction having its own value, that is called the 2. Minus sign is there, 0.5, and I have made the that mean integral of that portion, that is log base e of with the concern of x, and with the limit which we want to apply here, that is 0.10 to 2.01. Okay, so this is the solution of that part, and now we will put the value to the x. Okay, k final is equal to 2 minus 0.5. Here we are just applying the also bracket log base e, and the meaning of that 2.01 we have, minus of that base e, that is 0.10. Okay, so this is the bracket close we have. Here we are just also applying the property of that log m minus n. So log m minus n is equal to log m upon n. So we are just using here 2 minus 0.5, that is log base e, that is 2.01 is to be divided by 0.10. As we are just solving it, so we are just getting k final is equal to 2 minus 0.5, and we can write here that is log base e, that is 20.1 we have. And here we are just removing the Napierian log symbol, so we are just using the concept of the base 10 is here. So k final is equal to 2 minus 0.5 log base 10, and we are just approaching the meaning of the log base 10, that is with the concern of 2 multiplied by the 2.303, and the log base 10 we have, that is 20.1. Okay, so here we have the meaning of the 20.1, that simple natural log we are just calculating from the log table. So we are just getting that 2 minus 0.5 of that part, in the sense of if you're just completing solving, so we are just getting 0.5 into 2.303, and the meaning of the natural log we are just calculating from the log table, that 20 का अगर हम वन पार्ट निकालेंगे वहाँ से कैलकुलेट करके, so we are just getting 1.3 0.032. So it comes in the sense of that minus 1.5. So the K final which we are getting, that zero point 0.5 joule. So that's the first answer we have. Now the next portion we have to find out the meaning of the V final. Okay, so we are just using that kinetic energy final can be stated that half m V final square. Okay, so we are just making the formula that under root of that K final is to be divided by M. So whenever we are just putting in value all 0.5 joule, we have that 1. So whenever we are just solving the meaning of the V final, that comes in the part of the 1 meter per second. So this is the simplest representation of the problem we have in the part of the K final, as we have got the meaning of the K final, that is called the 0.5 joule, and the velocity final which we can easily got that the 1 meter per second. Okay, so here we have to be pay the attention that what kind of the topic which we are taking and how the numericals approach are available on the particular topic, so we should that follow them. Okay. Okay, thank you. Have a nice day.